Okay, everyone. This is a quick addendum to Lecture 32, which of course covered heat exchangers. So in class, in Lecture 32, we talked about some of the different types of heat exchangers that you might typically see. And what I want to do with this quick video podcast is extend that into calculation, right? How do you actually analyze heat exchanger performance? And we're going to do so using what's known as the Effectiveness NTU method, which is a very common method that is especially helpful when you happen to know what types of fluids are flowing into the hot and cold sides of a heat exchanger, as well as the temperatures of those fluids at the inlet of the heat exchanger. So before we get into that, let's quickly review what we mean by the inlet and outlet on different types of heat exchangers. So sketched over here on the right are two kind of classical sketches or sketches of two classical types of heat exchanger. The first, right, is what's known as a parallel flow heat exchanger, and is characterized by a hot fluid and a cold fluid that are flowing in the same direction. Right? What makes this an important factor is that right, the inlet for both the hot and the cold fluid is located on the left, and so we can, if we think about it, we know that, right, the purpose of heat exchanger is to bring the temperature of these two fluids closer together. So at the inlet, where neither the hot nor the cold fluid has yet undergone any heat transfer, we expect that temperature difference to be greatest. That is, the hot fluid is the hottest and the cold fluid is the coldest. And so for a parallel flow heat exchanger, right, the hot and the cold fluid inlets are located right next to each other. And then the hot fluid outlets and the cold fluid outlets are also located right next to each other. And so we define these four temperatures, THI and THO, for the inlet and outlet temperatures of the hot fluid, and TCI, TCO for the inlet and outlet temperatures of the cold fluid. All right. The next type is the counterflow heat exchanger, and this is a subtle variation, right? Same idea: hot fluid on one side of a surface, solid surface, and a cold fluid on the other. Heat flow should occur from the hot fluid to the cold fluid, but for this arrangement, our inlets are located on opposite ends of our heat exchanger. So our hot fluid inlet temperature, right, that is the hottest temperature of the hot fluid, is located away from the inlet of the cold fluid. And so in this case, the inlets and outlets of one side have simply been reversed. And so the important thing to take away from this is, right, the inlet and the outlet of a fluid, whether it's the hot fluid or the cold fluid, the inlet and outlet are defined with respect to the direction the fluid is flowing, not the location on the actual heat exchanger. So if you're dealing with a counterflow heat exchanger, the inlets are not necessarily going to be located right next to each other, and the outlets won't be located right next to one another. So, all right, what's typical, right, in an analysis is we might know what types of fluids we're pumping through this heat exchanger, and we might know what temperatures those fluids are entering the heat exchanger at. That is, it's quite possible that we'll know these quantities, right, the inlet temperatures of the hot and the cold fluid, as well as some information about those fluids, their fluid properties, for example. But we might not know the outlet temperatures. Maybe we do. In fact, in the example we're going to solve here in a second, we will. But what this does is this sort of situation where we don't have all the information is what gives rise to this Effectiveness NTU method. So to get into that, let's quickly introduce the notion of, right, the perfect maximum amount of heat transfer that could occur. So Qmax we'll go ahead and define as Cp.m. minimum times THI minus TCI. Okay, so what's going on here? Well, notice first this temperature jump, right? What we've got here is the difference between the hot and cold fluid inlet temperatures. So depending on whether we're talking about a parallel or a counterflow heat exchanger, these would be at different physical locations. But in either case, this represents the largest difference in fluid temperatures at any point in the heat exchanger, right? The hottest hot temperature and the coldest cold temperature. And this Cp times m dot, right? This can be thought of. Well, this quantity here, right, is in the book at least, just given the variable name capital C. We're not gonna do that in this example. I think it's too confusing to introduce more variables. But if you are reading the chapter and you notice that this Cp.m is gone, and instead there's a bunch of capital C's, just note that those two are equivalent. So this represents, right, if Cp is the amount of heat, or is the amount of thermal energy per unit mass per Kelvin, right, and m dot is the amount of mass per unit time, then what this quantity is going to represent is the amount of thermal energy per Kelvin per time, or the wattage per Kelvin, if you will. And the reason we have this subscripted minimum is that this quantity is probably going to be different for the cold fluid than the hot fluid. But the amount of heat transfer is limited by the weakest link, so to speak. It can only the amount of heat transfer between the hot and the cold fluid is limited by whichever of those fluids can accept or reject heat at the lower rate. So if we know m dot for each of the fluids and we know Cp for both fluids, then it's very easy to determine which one's the minimum and which one's the maximum. Okay. So from this Qmax, we can define the effectiveness of a heat exchanger, right, as Q over Qmax. And given what we know about Q and this new definition of Qmax, we could write this in one of two ways. Q can be written from the temperature jump in the hot fluid, for example. So this would be m dot hot times Cp. We'll just leave it with an H for hot. Cp hot times the drop in the hot fluid's temperature between the inlet and the outlet. That is the amount of, and this represents the amount of heat rate, or the heat rate out of the hot fluid into the cold one, over Cp dot m dot min times Thi minus Tci. Or we could write it using information about the cold fluid, in which case we would say m dot C times Cp C times, and the temperature jump here would be the temperature rise between the inlet and the outlet. So Ho minus Tci over the same denominator. Okay, and the reason we're able to write it in either of these two ways is that, remember, the numerators of these two expressions are equivalent. That is, the heat leaving the hot fluid has to enter the cold fluid. And so it's a Q in equals Q out situation. So we're satisfying the first law. So we can use either of these expressions. But what this means, right, what the useful aspect of this is that if we know the inlet temperatures of the hot and the cold fluid, and we know Cp and m dot for both fluids, and we know the effectiveness of that heat exchanger, then we can find Q. And from that we could find the outlet temperature, etc. So the way we would do so is we'd say that Q actual is equal to, right, epsilon times Cp dot m min times T hi minus Tci. So the real key here, and what we're not sure yet, is how to find this effectiveness parameter, right, epsilon. So if we went through all the literature and the history of analysis of heat exchangers, what we would find is that people have decided that epsilon, through dimensional analysis and the like, have determined that epsilon is effectively a function of two parameters. The first is what's known as the NTU parameter, and the second is the ratio CR, which is actually just defined as Cp dot m dot min over Cp dot m dot max. So if we know what m dot and we know what Cp are for both of the fluids, this guy's really easy to calculate. Okay, we just have to, it's just bookkeeping. But this NTU is the real unsure one, right? NTU actually stands for the number of transfer units, and it's a somewhat archaic term, but it's very commonly used in the design and analysis of heat exchangers. And so what people have done is they've compiled big, again, correlation tables. In other words, there are predetermined relationships between NTU and the heat exchanger effectiveness that we have the convenience of being able to just look up in a table. All right. So if we know C sub r, right, this ratio of minimum to maximum Cp dot m products, or Cp times m dot products, then the rest comes down to finding the correct equation that allows us to go between epsilon and NTU. So given one, we can calculate the other. So these have been assembled for us in two tables in the book. There's table 11.3, which allows us to, if we happen to know the NTU rating, then allows us to calculate epsilon. Okay. And table 11.4, which goes the other way. If we happen to know epsilon, we can find the NTU rating. And of course, both assume that we know this C sub r parameter. The last thing to note is the actual definition of the NTU. Right? The number of transfer units is defined as 1 over R total times 1 over m dot Cp min, where R total, don't forget, is the total thermal resistance that includes the convective resistance, the conductive resistance of the wall, and the convective resistance into the other fluid. It may also include additional resistance, thermal resistance created by, for example, scale or fouling of the walls of your heat exchanger. That is the accumulation of things like rust or calcium deposits or algae that tend to inhibit heat transfer by acting like an insulating layer. Those will be included in this R total as well. So this NTU and these effectiveness parameters, right, they talk about the same thing. They both sort of tell us how efficient a heat exchanger can be, but they do so using different metrics. So enough talking about the right, the way that we, or enough talking about the way we would calculate these things, like in sort of broad strokes. Let's do a specific example problem and show how the rubber meets the road, so to speak. So in this example, we're going to consider a cross-flow type heat exchanger. So this heat exchanger will have cold water that is being heated by a cross flow on the underside of this plate of hot air. So this is what's known as a single pass cross flow heat exchanger. The single pass refers to the fact that these two fluid streams cross by each other only once. Okay, they don't double back and go through subsequent layers of the heat exchanger. There are also 2-pass, 3-pass, 4-pass. If there's a number of passes as an upper limit, I've yet to find it. I've seen up in the tens of passes for heat exchangers before. So as I said, this cold fluid, right, is water with a flow rate m dot sub c of 3 kilograms per second, and this is hot air for which we don't yet know the flow rate or the mass flow rate. We do, however, know the temperatures at the inlet and outlet of both fluids. So the hot inlet temperature is 225 degrees Celsius. The hot outlet temperature is 100 degrees Celsius. Okay, so it drops 125 degrees. The inlet cold temperature is 30 degrees Celsius, and the outlet cold temperature is 80 degrees Celsius. So it warms up by 50 degrees. The last detail here is that we're not going to go into much. I won't belabor what this actually means. Is that the air side of the heat exchanger is what's known as mixed, and the water side is unmixed. Okay, this has to do with the practice of putting fins or other types of geometric features into the flow on one side or the other that can stir the flow up and distribute the temperature more evenly on one side. So what this is suggesting is that the air side has some sort of design feature that homogenizes the air temperature. So not important, or not terribly important for us to understand deeply right now, but this mixed on one side and unmixed on the other is important for us to know, because it'll affect which correlation we select here in a minute. So what we're supposed to find includes 4 quantities. Okay. First, the mass flow rate of the air. Second, the efficiency of the heat exchanger. Third, the number of transfer units, and then from that, we want to know the total thermal resistance across the total thermal resistance of the heat exchanger, including the convective, conductive, and any fouling resistances that might be sort of inherent in the system. So, to proceed, our first step, as it is with most problems, is going to be finding fluid properties. Okay, so in this case, we know the inlet and outlet temperatures of both fluids, and so our reference temperatures, those that which we look up fluid properties, namely Cp, is going to be halfway between the inlet and outlet temperatures of each fluid. So for water, right, we would say Tref of the cold fluid is going to be halfway between this 30 degrees Celsius and this 80 degrees Celsius, okay, which plants us at 55 degrees Celsius, which is 328 Kelvin, and at that temperature, the back of the book tells us that Cp, the cold fluid, that is water, is 4184 joules per kilogram Kelvin. Likewise, the hot temperature, our reference temperature will be halfway between this 225 inlet and this 100 degrees Celsius outlet, which plants us at 162.5 degrees Celsius, or 435.5 Kelvin. Okay. It's okay to round to the nearest whole number in this case. So in the back of the book, we should find that CpH is equal to 1018 joules per kilogram Kelvin. Okay, so now proceeding on to part A. What is m dot of the air? That is, what is the mass flow rate? So we're going to find this by using an energy balance. In other words, we're going to say Q in of the cold is equal to Q out of the hot, right? Which is just equal to Q. This is the same definition we gave before. In other words, Q is equal to m dot cold times Cp cold times the increase in temperature, Tc out minus Tc in, should work out to 3 kilograms per second times 4184 joules per kilogram Kelvin times, and then the cold fluid, right, the water, rises, undergoes a temperature increase of 50 Kelvin. And plugging these in, we should get 6.276 times 10 to the 5th watts. Okay, that's a big number. We're talking, 60. We're talking up in the hundreds of thousands of watts. Okay, so a couple hundred kilowatts, which shouldn't be terribly surprising. We're talking about also heating up. We're talking about heating water, which is has a high sort of heat capacity up by 50 degrees, and we're doing so to 3 kilograms of water every second. Okay, so this is a lot of heat that we are dumping into this water. And so from that, we would expect that we're going to see a pretty high mass flow rate of air required to accomplish this heating. So here's Q. We know that Q is also equal to m dot hot fluid times Cp of the hot fluid times the temperature drop experienced by the hot fluid as it goes from the inlet to outlet, which would be, from this we can then find that m dot h is equal to Q divided by Cph times Thi minus Tho. It should be that 6.276 times 10 to the 5th watts divided by 1018 joules per kilogram Kelvin times, in this case the hot air enters at 225 Celsius, leaves at 100 Celsius, so this is 125 Kelvin here. And this should give us a number of approximately 4.93 kilograms per second. Okay. So the mass flow rate of the hot air flowing through the system is nearly 5 kilograms per second, which is actually a huge number when you consider how lightweight air is. Remember, this is a big volumetric flow rate. So now that we've got that, right, so that's the solution to part A. So now that we've got that number in front of us, we can go ahead and find that quantity m dot times Cp for both the hot fluid and the cold fluid, figure out which ones are minimum and which ones are maximum, and from there move on to find the effectiveness and the NTU and then the total resistance. So Cp dot m dot for the cold fluid is going to be equal to, right, that 4184 joules per kilogram Kelvin times 3 kilograms per second, which works out to 12,552 watts per Kelvin. And CP dot hot, right, is going to be equal to 1018 joules per kilogram Kelvin times that 4.93 kilograms per second we just figured out, which should work out to 5018.74 watts per Kelvin. Okay, I'm going to go ahead and turn off those email notifications. So that ratio of the so at this point, right, just a quick comparison shows us that we don't need that 7.4. We'll go ahead and just round that up to the nearest whole number, and so we can see clearly that this is our minimum. That is that the hot fluid constitutes the minimum quantity, and that the maximum quantity is the cold fluid. In other words, the airflow is the weak link or the limiting factor in the amount of heat that's actually flowing through the system. Okay, so two things we can calculate now. First is this C sub r value, which is going to be, right, the ratio of the minimum quantity to the maximum quantity. So this will just be 5019 over 12,552 with the units canceling, and this works out to approximately 0.4. Okay, so we want to hold on to that, keep that in our back pocket because we'll need to use it later. And then the next thing we can calculate is the effectiveness, right? So epsilon is going to be equal to Q over m dot Cp min times Thi minus Tci. So we can go ahead and write this out as our actual heat rate, 6.276 times 10 to the 5th watts over, right, m dot times Cp min is going to be our 5019 watts per Kelvin times 225, that is the hottest hot temperature, minus 30, that is the coldest cold temperature. Okay, and if we plug all these numbers in, what we're going to find is that epsilon is equal to 0.641. Okay, so there's our solution to part B. Okay, so next up, we're going to turn to table 11.4 in the book. So I recommend you get your book out in front of you, find table 11.4. It's in section 11.4 as well. And what this is, it should be titled Heat Exchanger NTU Relations. Okay. In this case, we're looking for the number of transfer units. We have the effectiveness, and we have a bunch of information about the flow. And so this table will give us the a precompiled set of equations that we use to find the number of transfer units. So what we're looking for specifically, let's look at the characteristics of this particular heat exchanger. Okay, so this is part C. It's a single pass cross flow. Okay. We have C max, right, or that m dot Cp max corresponds to the water phase, which is unmixed, m dot Cp min, right, is tied back to the air phase, which is mixed. Remember that mixed and unmixed we talked about at the very beginning, the definition of the problem. And so from this, right, we can go down this list of relations in table 11.4. Parallel flow, no. Counterflow, no. Cross flow, single pass. Okay. And if we look at Cmax and Cmin mixed or unmixed, in both of these cases, right, we get to pick which one's mixed and which one's unmixed. So we have in this case that the Cmax is unmixed and the Cmin is mixed, which corresponds to equation 1134b. Let me make sure that's correct. Cmin, yep, is the air phase, and the air phase is mixed. Yes. Okay, so equation 1134b, which says the NTU, number of transfer units, is equal to negative 1 over this C sub r times the natural log of C sub r times the natural log of, let's go ahead and put some square brackets on here, of 1 minus epsilon plus 1. All right, so give me a moment to dial this into my calculator. So we're working with, right, that C sub r is equal to 0.4 and epsilon is equal to 0.641. So this is going to be negative 1 divided by 0.4 times natural log 0.4 times natural log 1 minus 0.641 . Okay, and what I get is a value, NTU value, of 1.318. Okay, so not a whole lot of physical meaning to attach to this. This is just a number to us right now. But let's not forget that we can from this number calculate some stuff that actually has some physical significance. So this is the solution to part C, and what we're left with now is part D, where we want to find, right, the total thermal resistance. So to do this, recall that NTU is defined as 1 over R total times 1 over m dot Cp min. All right, so this is pretty straightforward. In other words, R total should be equal to 1 over the number of transfer units times 1 over m dot Cp min. And if we want to go ahead and plug those numbers in, it'll be 1 over 1.318. That's 8 times 1 over 5018 watts per Kelvin. Should be 1.512 times 10 to the negative 4th Kelvin per watt. And that wraps up the solution. So, a few parting thoughts here. What might we use this for? Well, if we happen to know information about, for example, if we happen to know a couple of the convection coefficients for the fluid flow on one side or the other of the heat exchanger, knowing the total resistance, right, might allow us to then pick apart and figure out what the other convection coefficients are. It might allow us to, if we were to calculate, go through this process several times during the life of a heat exchanger, we might see that this R total number begins to climb as you end up with scale or calcium or mineral deposits that are accumulating on one side of the heat exchanger. This is, as I said, what's known as fouling. And if we were designers, right, this would allow us to come at it from a lot of different ways. If we happen to know the inlet temperatures of the fluid, we could go through this whole process iteratively and figure out the outlet temperatures of the fluid as well as the efficiency in the NTU and the total power or the total heat transfer rate. So I'll leave it at that. I thank you for watching. There will be one simple heat exchanger problem on the upcoming homework. Hopefully this has given you some structure on how to approach those problems, though you may need to do a bit of supplementary reading from particularly section 11.4 in the book.